Now that we've had a chance to work on relations for a little while, I'm going to talk a little bit about some different types of models to help us understand relations better. Now, some of these models are going to be ones that I made up. Some of them are going to be models that you can find in Uncle Ted's book. Either way, they are all helpful for understanding relations. So we're first going to describe some of these models and illustrate them with examples. We're going to see how different models can give us a different way of understanding a given relation. We're also going to see how some models can lead to different types of relations. All right, so here's a model that can be applied to any relation, and I call that the social media model. And so you can think of a relation R as expressing some kind of social media relationships, like if you have something on Instagram or on Twitter. We can say that when A is related to B, that could be thought of as A follows B. So note that if A follows B, it is not necessarily true that B follows A, both in a relation in general and on Instagram too. I know because nobody follows me. All right, so let's think about the less than or equal to relationship back in the old days. So here, when we say A or B, that means that A is less than or equal to B. We know that 2 is less than or equal to 5. That means 2 are 5. And so we could think of it in our model that 2 follows 5. In fact, all small numbers follow all the larger numbers, but not the other way around. So 5 does not follow 2. So here's a more visual model for relations. This is called the directed graph model. This is you can find this one in the textbook. Suppose we have a relation R between the sets A and B. If A is related to B, A or B, we can express this as A with an arrow pointing from A to B. So here's an example of a relation, and actually here's a relation that's a little bit different than the ones we're used to seeing. I'm literally just writing the relation as a set of ordered pairs. And so we have the ordered pair way of looking at this relation according to the definition. Now let's see how this is going to look if we write it as a directed graph. Well, the first thing to note is let's look at our first ordered pair. That's here's what the directed graph one is going to look like. Our first ordered pair is 1, 5. That means 1 is related to 5, and as you can see, I've illustrated that with 1 pointing at 5. The next one is 2, 8. That means 2 is related to 8, and so we write 2 and 8 with an arrow going from 2 to 8. And the next one is 3, 7. Again, we have 3 and 7 with 3 pointing to 7. We don't have to have the arrows going from left to right. As you can see in this one, the arrow is going from the top one to the bottom one. Now the next one is 1, 2, and notice that 1 and 2 are already part of our picture, part of our directed graph. We don't have to write them again. We can just take the existing 1 and 2 and write an arrow or draw an arrow from 1 to 2. And with 3 and 5, it's the same thing. We already have 3 and 5 in our graph. We just have to draw an arrow from 3 to 5. And there's our directed graph model for that relation. And here's a model that I want to look at in some detail. It doesn't describe every possible relationship like the directed graph model did and like the social media model did. This only applies to certain types of relations. So this is a team model. And so what I want to do is I want to think of what types of relationships do you have when it is thought of as a team relation. In other words, where you have a situation where you have different teams playing in some sort of competition. And in this case, I want to say that A is related to B when A and B are on the same team. So, and the people that we're talking about in this relation are just the people who are in the competition. If you're outside the competition, the relation is undefined. So we're only talking about people who are actually playing on one of the teams. So just note team relations, they behave differently than other relations. In fact, they have some properties that most other relations do not. So for instance, every person is on the same team as themselves in this team. So that means every person is related to themselves under the relationship. In other words, A are A for all people A. And again, that is not true of every relation. So try to use some imagination to think if you can think of a relation where that is not the case. If you can't, you can ask me in class. If it happens that A is on the same team as B, then it automatically happens that B is on the same team as A, right? Or if we're thinking about that abstractly, if A is related to B, then B is related to A. We've already had some relations that don't fit that one. In fact, one of our very first ones, the love relationship. It's possible that A could love B, so A are B, but B does not love A, so it's not true that B are A. And then the third one is if A is on the same team as B, and if you have B being on the same team as another person C, then it has to be that A, B, and C are all on the same team. In other words, then A is on the same team as C. And again, with your random relations, this is not going to be the case, only with special relations. And so if we want to state this more abstractly, it says if A is related to B, and if B is related to C, then A is related to C. And these three properties are the fundamental properties that make up an equivalence relation. All right, so here are some properties inspired by our team relation. So our definition is going to be for these properties. So let A be a set, and let R be a relation that is defined on the set A. We say that R is a reflexive relation if little a is related to little a for all little a in the set. We say that R is symmetric if whenever A is related to B, then B is related to A. And we say that R is transitive if whenever A is related to B and B is related to C, then A is related to C. And all three of these properties are the ones that we were talking about in the previous slide with respect to the team relation. So I'm going to sort of try to describe these, give you a visual of what these properties kind of tell us. That was a verbal description of what the properties are. Now I want to show you in pictures using the directed graph model. So I'm going to have two types of arrows. One are the solid arrows, and those are the arrows that we get from our assumptions. And one of the things, if we look back at that definition, is in every one we have some things that we assume and some things that follow from that if we have that property. So the solid arrows are going to be the assumptions, and then I'm going to have some dashed arrows that are what our conclusions are. So the solid arrows are what the arrows that we are assuming exist, and the dashed arrows are the arrows that exist because of those solid arrows that we're assuming. All right, so for instance, if we're looking at the reflexive property, there are no assumed arrows at all. In fact, all that is assumed from our reflexive property is that we have some element in our set, little a. And what we can conclude then for our dashed arrows is that A is related to itself, which means that there's an arrow that starts at A and ends at A. So all we're assuming is that A exists, and then we can conclude that there's a dashed arrow from A to itself. So for symmetric, what we are assuming is that A is related to B. That's why we have that solid arrow. And then what we can conclude is that B is related to A. So if A is related to B, then B is related to A, which means our dashed arrow is going to go from B to A. And then our transitive property is very similar. The if part is we assume that A is related to B. We assume that B is related to C, and then we can conclude that, dashed arrow, A is related to C. So now we're ready to define what equivalence relations are, and it's not going to be anything earth-shattering. Again, we have a set A, and we have a relation on that set A. We say that R is an equivalence relation if it satisfies all three of those properties. It's reflexive, it's symmetric, and it has the transitive property. So now that you've got an idea of how these relations work, try working on the activities for more relations on the PDF file included with this video. Note that that more relation was also included with the other video, so if you weren't able to solve all those problems, maybe these models can help you work with those.